Okay, so we are talking about neural network methods. So we learned basically how to build a multi-layer perceptron for text classification, and how to train word embeddings, how to represent sequences for text classification, and we learned how to predict structures, right, last week. So this week, we learn how to represent structures because you want to make use of the structures. So these are some examples of structures that could be useful. We learned how to give part of speech to a sentence. We learned how to give dependency trees, constituent trees, and we also saw some structures in week 1. For example, relations between entities. They represent knowledge. Okay, these structures can be useful for performing downstream tasks in NLP. And the thing is, how do you represent them, right, so that different tasks can make use of their features? And we learned 3 main things this week. So the first is how to represent trees. Okay, the second is how to represent arbitrary graphs. And the third is how to represent text structures. Okay, so let's first look at trees. You know, the dependency trees and constituent trees, they are all tree structures, right? And if we have the syntax of a sentence, right, it can help us to do disambiguation on syntax-aware tasks. Okay. So, and you can tell me, wait, I can implicitly learn syntax by just training my sequence encoder, right, as you showed me last week. But here we will show that encoding explicit syntax can give complementary features compared to encoding implicit syntax, because as I mentioned several weeks ago, the neural representations, they are not so interpretable. So even though you learned a implicit syntactic representations, you don't really know whether they truly represent the syntax you want. Okay. And when we build a tree representation, the first question we ask ourselves is, okay, how can we use neural networks to learn tree-level context features, right? So just as we discussed for sequence representation, we need to learn word-word relations within n-grams and also globally, right? So there have been people thinking about CNN, for example, for representing trees. But let's go straight to recurrent neural networks, because they can extract more global context as compared to convolutional neural networks. So we learned how to build an RNN for representing sequences. And to represent trees, a clever or a reasonable start is to review sequences and tell the difference between sequences and trees, right? So that we can extend our sequence RNN. And here, I show you the similarities and differences between sequences and trees. So they are all directional, first of all. in the sense that for sequences, you can go left to right, right? And for trees, you can go top down or bottom up. They're all sequential. But the difference is that I showed you different sorts of trees. Trees have multiple subnodes for each node, all right? So sequences are just one row. You have only one successor or predecessors for each node. I think that's the main difference, okay? A sequence can be seen as a tree, after all, right? It's a tree without multiple branches, just one branch tree, okay? So when we build an RNN, okay, for sequences, we just go left to right, and we define an RNN step to consume each input, okay, and update the current state. Now, when we think about an RNN for trees, shall we go top down or bottom up? That's the first question, right? Do you want to go top down? Or do you want to go bottom up? I guess most people want to go bottom up, right? Because each node has a subtree. If you go bottom up, the node representation will contain everything about its subtree. That makes more sense, okay. Okay, so let's first agree, right? I think most people agree. And then the next question is, suppose we go bottom up, then what changes should we make, okay, from a sequential LSTM so that our node can absorb its children information, okay? Now here, we found that the key issue, right? The key issue is how to integrate information from multiple children, okay? So let's do the extreme thing. If we just simply sum up information, right, from all children, if we brute force sum up all the child node into one node when we represent each node, then the tree LSTM will become a sequential LSTM, right? At least locally, right? So multiple child node summed up into one. And then so this bottom-up step is just a standard RNN step, okay? That's too simple. That doesn't tell us the difference between subnodes, okay? So we need something more flexible. Okay, I will discuss two variants to tree LSTMs, okay? One borrows the idea of summing up children, but does something more fine-grained so that it still differentiates children. The other assumes that the tree is an n-ary tree. Take binary tree, for example. If the number of children is fixed, then we can sort of extend the RNN step and make sure that each children in the n-way branching node can be differentiated. Okay. So let's first look at the child sum tree LSTM. So we have agreed we have to do things bottom up, okay? Instead of left to right. And then we agreed that we should, in principle, sum up children information, okay? And somewhere in the equations, we differentiate different children. But then for arbitrary trees, we have to first decide the order in the bottom-up direction. For example, if you give me a dependency tree, okay, here I use dependency trees to illustrate. Then we need to change it a little bit, okay? Rather than placing things in a word order, I need to take the root of the tree, okay, and let different subnodes form in a hierarchy like this, okay, so that we can have the layer structure. And why don't we just define the bottom layer as layer 1? I say t equal 1, okay? And then one layer up t equal 2 until, okay, whatever the root node is, okay? So that we naturally have the time sequence, time step 1, time step 2, time step 3, okay, bottom up. So, you know, at each time step, we also have different nodes, right? So, time step 1, I have node 1, 2. Time step 2, I have nodes 1, 2, 3. Time step 3, I have node 1. Okay? So I put time steps as t and put the index within each time step as I. So I have like x31, x21, 2, 2, 2, 3, like x1, 1, 1, 2. So in this index. If I have this index, okay, I'm basically turning x1 to xn into xti, the subscript and superscript, and I'm turning ht, the corresponding hidden node, into hti. All right. So I want each hti to contain information about its subtree. All right. So I want to build an LSTM to this end. So for any node, okay, I denote as xti. It has subnodes. So I denote as hti minus 1. Why ti minus 1? Because I'm doing bottom up, right? So the subnode has a lower time step index, okay? And then what is this? CTI1, CTI2, CTI, MTI. Okay, so this is just the index of the child nodes. Okay, so I use CTI1 to represent the index of the first subnode on TI. For example, if you say take x31, okay, t is 3, I is 1, right? So this C311 is what? It's 1. It's the first node on the second row, okay? So this is just a index mapping. And so this MTI means how many children does the like tth layer, ith node have. So for example, if I say M31, okay, the third row first node, which is the root node, okay? So M31 is 3 because it has 3 children, okay? So I'm just turning this index in this way. All right. So it doesn't matter for understanding the rough idea. Now we want to sum up the children. Okay, in particular, I just try to sum up the hidden nodes into one previous hidden state. Okay. But how do I differentiate the children node? I will have a different gate computed for different children. Okay, so here are the equations. These are the most crucial equations for understanding this child sum tree LSTM. So first, I make all the child node hidden states into one previous hidden state. I call it ht minus 1i, okay? So it's the previous hidden state for hti. How do I do it? I just simply sum up all the children hidden nodes. Let's still take the root, for example. Here, I want to calculate its hidden previous hidden state. Okay, I just sum up this hidden state, and this hidden state. And that's the previous hidden state. So I want to calculate the previous hidden state for this node, then I just sum up these two nodes. Okay? So I want to calculate the previous hidden state for this guy. What is it? Okay, I calculate a special initial hidden state for its previous hidden state. Just like a standard LSTM, right? You have an initial state. Start state. Okay, so the hidden are dealt with. So let's look at the cell. I guess you still remember the cell state computation for standard LSTM, right? So it's a input gate times an input representation plus a forget gate times the previous cell, right? So now I want to have a separate gate for each child node, okay? So it becomes like this. I still have a G, okay? G representation for the input, which is a 10H activated neuron, okay? So this neuron takes the previous hidden state, as I showed you here, the current input, maybe the word embedding, okay, of the current word node, okay? So G is computed in the same way as for sequential LSTM. And then the cell state is the sum of the input gate times G, okay, Hadamard product, right? Plus, for all the child node, a separate gate for this child node times the child node cell. All right? So this is the difference, okay? One aggregated hidden and a separate gate for each child node. So how do I calculate the gates? Here it is. The input gate is nothing different from the that of the sequential LSTM, okay? Forget gate is also very similar to the sequential case. However, you can note that there is a difference, okay? So the difference is in the H, you know? When you calculate the forget gate for a cell, you use its corresponding hidden state, okay, rather than the aggregated hidden state. So I'm using H, T, I minus 1, C, T, I, J, okay, for the forget gate J, for, okay, and the remaining is the same. So the X is still the current input, XTI. All right. So this will differentiate different children because each child, the gate for each child is computed using the child's hidden state. All right. Okay, so that's the difference. And we're able to compute the cell. Now the output is exactly the same as the output for sequential LSTM. I first calculate an output gate, okay, using the previous hidden, the current X, and then the hidden is the output gate times sigmoid of the cell. So this is exactly the same. Now, if I put all these equations together, you have this. I first calculate one aggregated previous hidden, all right? And then I calculate an input representation using the aggregated hidden. Then I calculate an input gate using the aggregated hidden and a separate forget gate for each child node by using the child node hidden, all right? Having this gate, I have the cell, recurrent cell, okay, in the third equation. After having the cell, I compute the output gate and the hidden state, okay, using the cell. So this is the child sum LSTM. All right. if we have a binary tree, we don't even have to aggregate the hidden nodes. Why? Because now I know how many children each tree node has, okay? So if I know how many children each tree node has, I can name them, right? Jason, John, etc. Because I know the number, okay? In particular, if I assume this is a binary tree, okay, because we can be general, okay, we can say that it's an n-ary tree, but I just take binary tree without losing generality, okay? So each node will have a left child and a right child. Why don't I just name the left child L and the right child R, okay? And then I can index them, okay? Still, let's have the like layer index bottom up, okay? T equal 1, 2, 3, etc. Bottom up. And then I can say for each node HTI, okay? I can have HTI minus 1, BTIL. What does BTIL mean? It's the layer-wise index, okay, for the left child of HTI, you know. Similarly, BTIR is the layer-wise index for the right child of HTI, okay? So we can differentiate the hidden states using those indices. And similarly, we can differentiate the cell states. And then how do you calculate the recurrent cell? We can have a separate forget gate for the left child and the right child. Here it is, okay? I just, for each node, HTI, okay? I calculate an input gate using this equation. You can see that rather than having an aggregated previous hidden state, I am having the left child hidden state times a specific matrix, okay? And the right child previous hidden index times a specific matrix, okay? And also I put the cell state here. Okay, this never happened. Why do I put the cell state here, okay? I just want to show you a variance, okay? And of course, I'm faithful to the original paper, but here I show you that it's possible. When you calculate the gate values, you can put the previous cell values in, okay? It's also possible for sequential LSTMs. But because I want to simplify things, I didn't introduce it, okay, 2 weeks ago. All right? And these equations are called peephole connections. You can remove the cell states, okay? Leaving only 3 terms in the input gate. It's also okay. But if you put the cell states here, it's called, you added the peephole connection. Okay, and similarly, for the forget gate, for the left child, I also put the left child hidden state in, the right child hidden state in, the left child cell state in, and the right child cell state in. Why am I able to do that? It's because I know there are only 2 children, right? So if I don't know the number of children, I cannot have a separate W for each of them. I have to aggregate them, or I have to use the same W for all of them. All right. Okay, so this is the only difference. Okay, you can have a different model parameter when we calculate the gate values for each children. And then the remaining of this binary tree LSTM is boring. It's the same as the child sum LSTM. Okay, now that you have a left gate, a left forget gate, you have a right forget gate, you know, you can calculate a G just as before, okay? And then your cell is the input gate times G plus left forget gate times the left child cell and the right forget gate times the right child cell. Okay, a three-way gating mechanism. And then the output gate and the hidden state is computed just as the sequential LSTM and child sum tree LSTM. All right, that's it. Now, good. You say, when I have a tree LSTM, okay, I can represent trees so that every node contains information of all its subnodes. Now, when I have a sentence, I can use a dependency parser, okay, to derive its dependency syntax, and I can use the tree LSTM to represent it, okay. But here are two things that I want to say. The first thing is for sequential LSTMs, right? We had a bidirectional version. I can do the sequential LSTM from left to right and from right to left. For tree LSTMs, I only have bottom-up information. Can we integrate bottom-up information and top-down information so that every tree node contains the whole tree? Okay, in other words, can I have a bidirectional tree LSTM? The answer is, of course, yes. So how do you get the top-down tree LSTM? Let's find a tree. Here is a tree. It turns out that when you do the top-down recurrent steps, you realize it's just a standard sequential LSTM. Because when you go to any node, from the root node, there's a unique path. There are no branches. No node has two parents, right? No tree node has two parents, right? So the top-down tree LSTM is a standard sequential LSTM. Because of this, okay, you can combine the top-down component, which is a sequential LSTM, and a bottom-up component, which is a tree LSTM. Okay, combine the hidden, and you get a bidirectional tree LSTM. So this is the first thing to note. The second thing to note is, okay, I can represent a dependency tree according to a tree structure. But if I do this, do I lose the sequential features? Okay, I don't want to lose n-gram information. I don't want to lose maybe the subsequence information. Okay, so if I use a tree LSTM, I only keep the tree. I lose the sequence. Can I integrate sequential LSTM, tree LSTM? There are two ways you can do that. Okay. The first way is, now you're given a sequence. You first encode it with a sequence LSTM or whatever sequence encoder. Okay, and you get a set of hidden state for each node. All right, and then you feed this hidden state into the tree LSTM to further extract tree level features. All right, you can do this. This is called stacking. You say, can I stack a sequence on top of a tree? Yes, you can, but it's rarely used. Okay. I guess the results are empirical. And the second way is, so this is a stacked mode. So this is a parallel mode. You separately encode the sentence using the tree information and the sequence information. And in the end, you get a hidden from the tree LSTM, you get a hidden from the sequence LSTM. You just concatenate the two. This is more like a parallel, right? Okay. The two complement each other by abstracting different context. You can also do that. And I give you two examples of using TreeLSTM to solve NLP tasks. So this is a task I show you, sentiment analysis. But this sentiment analysis is not done in the sentence level, but done in the phrase level. The data set is called the Stanford Sentiment Tree Bank, or SST. It has a lot of movie review sentences. Each sentence is parsed into a constituent tree. Okay? And the constituent tree is normalized into binary branching form. All right? And you want to predict the sentiment label on every phrase. For example, the last two words, intelligent humor, is a positive phrase. Okay? However, if you move up the tree, you realize there is a doesn't, okay, phrase. When this is semantically composed with care about, blah, 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 the positive thing, everything becomes negative, okay, when the information propagates onto the top of the tree. So this is a nice chance, right, for you to model semantic composition. So you can start from every word, okay, start from the word embeddings, and use a TreeLSTM to represent the hierarchical structure bottom up. Okay. Then when you have the representation of every node, you can do a binary sentiment classification by adding a classifier, right? And then the SST dataset has a human label, not human label, but like semi-human label on every phrase, okay? The sentiment label, which can be used to train this hierarchical phrase classifier. The second example, okay, is relation extraction. The task is to predict the relation between any two entities in a sentence, right? Of course, how can you do that? We learned dependency parsing last week. So this is very similar to dependency parsing, okay? So if you have a sequential sequence encoder, then you can feed the sentence into the sequence encoder, right? And then you can take all the entity spans. You can think about how to represent the spans. We also learned them last week, right? We can use by LSTM, beginning and end hidden. We concatenate them together to represent the span. Or I can use a query to do attention over the span. Okay. After you can represent the entity spans, how do you predict the relation? Maybe you can put the two spans together, right? And add a classifier layer on top of that to predict the relation. So these are within the knowledge we had last week. So how do we further add tree information? Now it turns out that the dependency tree is super helpful for relation extraction, okay? Even in the neural age. So we can parse the sentence into a dependency tree, okay? So on top of the sequence representation, we can further calculate the tree representation. And then we can integrate, okay, tree-based features of the entities for relation classification. It turns out empirically that adding not only the two entity span representation, but also their lowest common ancestor word representation, okay, gives strong results. What's the intuition? The intuition is that the lowest common ancestor is typically a predicate, okay, that dominates the correlation between the two. entities. For example, in this sentence, okay, Yates was born in Chicago. If we want to detect the relation between Yates and Chicago, okay, we found that their common ancestor was born. Okay, so if we have features from born, then it clearly tells this is a birthplace relation. Okay. All right. So I gave you 2 examples for using triad stems. Let's move on. Here is a semantic graph. It's the meaning of the boy wants to go. Okay? And you can see that the boy is the subject of want. The boy is also the subject for go. Okay? And want is a verb that modifies go. So these 3 edges makes a graph structure rather than a tree. And I want to represent the semantic graph. Okay? How do I do that? So if you look at the semantic graph, what's the difference between the graph and the tree? So this is a directed acyclic graph, DAG. Okay? For DAGs, you can have loops, but these loops are directional. Okay? Not a loop back, but a unidirectional edge set forming a loop. So DAG is a slight extension of the tree. It's directed. Each node can have more than 1 children and also more than 1 parent. Okay? So DAGs are a slight extension to trees with multiple parents. How do I represent DAGs? I can borrow ideas from child sum triad stem. Okay? Now let me consider every node. Every node can receive information from multiple child nodes. Okay? Why do I still have the idea of child node? It's because this graph is directed. Once we have a directed graph, we can have a layer concept, you know. I take the last node or the node without outgoing edges as the last node, okay, as the first layer. And then we can recurrently discover the layer structure until the node that has no incoming edges. Okay, that's the top node. Okay, it's a directed graph. Once we can have the layer structure, I can do the same as child sum triad stem. I can observe every node. Okay, and I recurrently define the information integration function from all its subnodes. So I can add the hidden node of its subnodes together into one previous hidden node. Okay? And then I can represent the input G by using tan H of a neuron that takes the previous hidden and the current input. And then I can define the input gate I using the previous hidden, aggregated previous hidden, and I can define a forget gate for every subnode by using the subnode hidden. Okay? Then how do I aggregate subnode information into the current node cell? Look at the 5th equation. The current cell is equal to the input gate times the input representation plus, okay, the aggregated cells, okay, each having its own forget gate. I can do that, right? Because every node can have multiple children. I just sum them up. And then the output gate and the hidden computation is exactly the same as TRI-STM. That tells the DAG LSTM. But wait, some of you show me the expression. So this is exactly the same as child sum tree LSTM. But for encoding DAGs, what's the difference? Why do we have exactly the same equation as tree LSTM? This is because it's directed, right? So I only consider collecting information from children. I never collect information from parents. Okay, so, but if you look at the token boy, it has two parents. It has two parents. So what does it mean? It means that the same node will contribute to information collection to both want and go. Okay? So the information is duplicated. That's what having multiple parents mean. Okay? This is not a tree, this is a DAG. So the node boy will contribute to both the computation of go and the computation of want. All right. And then information, of course, will backpropagate, you know. To boy from both go and want. That's the difference. So how do I use DAGs for representing things? Here, let me give you one simple example. Okay, it's how do you represent Chinese sentences? Okay, so you know a Chinese sentence is written as a character sequence, right? And for linear models, we have to do a pipeline. We have to first do Chinese word segmentation to chunk the sequence into a word sequence. I didn't have time to tell you chapter 9 in the first edition, which discusses semi-CRF and segmentation algorithms. If you're interested, you can read them, okay? But, you know, if you do word segmentation and represent the Chinese sentence as a word sequence, then you have a problem. So if your segmenter makes errors, then your representation will suffer from incorrect words. This is called error propagation. In chapter 11, we discussed that, but unfortunately, I didn't have time to show you in class. But last week, we learned neural representations, right? So if we're a neural model, then we can just represent the character sequence. Then word information can be implicitly learned. Just as part of speech information can be implicitly learned in a set of word representations. Okay? But as I discussed earlier, this kind of implicit word information cannot be interpreted. And they might not be the words that you want. Okay? Then how do I strike a compromise between character-based Chinese sentence representation and word-based Chinese sentence representation? One simple idea, okay, is to have a dictionary at hand. Given any character sequence, I just match the dictionary and take out every possible word, even if it might not be the correct segmentation. For example, if I give you this word, 长江市, sorry, 南京市, 长江大桥, okay. You don't know whether it's Nanjing 市, Nanjing city, Changjiang Yangtze River, 大桥 Bridge, or Nanjing 市长, Nanjing Mayor, 江大桥. Okay, so it's ambiguous. Then why don't you just put all the possible words here? Okay, and then this forms a lattice, because from every point to every other point, there might be every different word character compositions. Okay, so this is a lattice. Okay, and I put like Nanjing, Nanjing 市市长. Okay, Changjiang, Changjiang 大桥, etc. All these words from the dictionary into this, and it's a lattice. And we can use a DAG LSTM to represent it by treating word as node and characters as nodes. Okay, and we can do a bidirectional DAG LSTM, so that every word, every character will contain both character sequence information and word sequence information. And every word can contain word information and character information as well. So in the end, if I use the character representations for downstream NLP, then we can automatically learn which words are more useful. Let's further discuss the representation of graphs. So far, we discussed trees and DAGs, but there can also be cyclic graphs. It turns out that in many useful structures, we can observe the real cycles, directed cycles. This cyclic structure brings us an important difference, which is we cannot define a natural time step anymore. Because there is a cycle, then who is the root? Who are the nodes on different levels? You cannot do that anymore. All right. So how can you solve the problem? All in all, the whole reason you want to define an LSTM is to allow words, or nodes, to exchange information with each other, right? So no matter whether we have a natural order of the nodes, we know they are neighbors, right? So if we say we can define a sort of time step where every node can collect information from its neighbors, okay? No matter the neighbor is its subnode or parent node. There's no concept of subnode and parent node anymore because there are no natural order anymore. But we have neighbors with maybe incoming edges or outgoing edges. They're all neighbors, right? And every node can collect information from them. So with this thinking, we can define a new definition of time step. The time steps are orthogonal to the graph. Okay? So in other words, we can take continuous snapshots to the graph. In between two snapshots, we define a mechanism for every node to collect information from its neighbors. All right? That's the basic thinking of graph neural networks. And this information exchange is done between the node in the current time step and its neighbors in the previous time step, as I show you in this picture. And every node can do the information collection simultaneously. Okay. So this is called message passing. We can still define the hidden state notations as HTI, but here I is the index of every graph node. Okay, we don't differentiate node by the layer, but this T is the Tth iteration or Tth snapshot. So every graph node xi will have hi1, hi2 until hi capital T, depending on how many iterations we want to go. Okay, so at every iteration, this hi T will receive message from all its neighbors, like h omega I. I use omega I to define the set of neighbors for hi, okay? So ti minus 1. So that's the basic idea. And of course, given this information exchange scheme, we can use different functions to collect information from neighbors. We learned RNN, CNN, and SAN, and we can apply all of them to graph neural network. So if I apply RNN to graph neural network, we arrive at GRN, graph recurrent network. Okay, so how can we parameterize it? Again, let's define the neighbors of node I as omega I, okay? So we can borrow idea from like child sum tree LSTM. And I say I aggregate the hidden state of all its neighbors in the previous time step into one message, m t minus 1I, okay? So it's like a child sum. And then the current hidden for node I, okay, denoted as HTI, node I time step t, is just a standard LSTM step by taking the aggregated hidden MIT I minus 1, t minus 1 as the previous hidden state, and I calculate a current input xi. This xi will represent the information of the graph node itself. Okay, so xi can include the node information and edge information. This is an example how do I encode xi. Okay, so xi is I first concatenate the embedding of the current node and the embedding of each neighbor node and the edge embedding, LIK. Okay, LIK is the edge between node I and node K. Maybe it contains direction information, edge direction, and edge label. Okay, I didn't say what kind of graph it is. So the label can be a dependency label, can be a semantic relation label, can be a knowledge whatsoever. But this embedding table is obviously different from the word embedding table. So I name it embed E. Okay? You say you didn't teach me how to embed a graph edge. But by now you should be able to do it yourself because you've learned character embedding, part of speech embedding, dependency label embedding, and so on and so on. Okay? So as the equation shows, I embed the node, okay, plus all of its neighbors, plus the edge information, and I pass them through a single neuron, and I aggregate them together as the node representation X. Okay? And that gives us a naive version of graph recurrent neural network. All right. I aggregate the hidden, I aggregate the input, and I use a single LSTM. But I can do more. Okay. If I want to differentiate incoming edges and outgoing edges, how do I do it? Oh, I can collect information from both kind of edges separately. Okay, so I got an M incoming and M outgoing. So the M, the message I have, is the concatenation of incoming hidden and outgoing hidden. Similarly, I can collect input information from incoming edges and outgoing edges, and the input representation is the concatenation of them. That gives us a more advanced version of graph LSTM. That already works very well. But this is not tree LSTM, right? Tree LSTM has a separate gate for every neighbor. Now I'm doing the naive thing. I'm not differentiating neighbors, but aggregating them. Can I have a separate cell for every neighbor? Yes, you imagine. The first three equations are my naive version, right? So it's like I brute forcefully change a tree or a graph into a sequence, sort of like that. But if I do more fine-grained way, I can go into the LSTM step function, you know. I can define a different cell, okay, for different neighbors. I can do that, right? Just by following child sum LSTM, right? I can still aggregate the neighbor hidden into one hidden, but I can calculate a different gate for different hidden. So within LSTM step, I can change the calculation. All right. Are there more variants? I leave it to you. And this contrast shows a very good example how you can practice your neural modeling techniques. But if I use CNN to collect neighbor information, I got GCN, Graph Convolutional Network. What is GCN? You know, the first two rows shows how to aggregate neighbor hidden into a message and how to aggregate the graph structure into an input, right? So RNN uses an LSTM step to calculate the current hidden. But the naive GCN can change on the LSTM step into a like convolutional function, like this. Okay. A convolutional feature is just a standard feed-forward neural network. So, if you expand this information a little bit, okay, you can see that that is equivalent to what? To multiplying every hk t minus 1, multiplying the hidden state of every neighbor with Wm, right? And that's exactly what a convolutional filter does, right? So that's the reason why I call it a convolutional function. Of course, we can build different things on top of the naive version. For example, we can differentiate different edge labels. And here, you know, when I calculate HTI, I use sigmoid over an aggregation of convolution filters, okay? So for each neighbor, H k t minus 1, where k is an index in omega I, the neighbor. Okay, I apply a different weight matrix Wm. So basically I can have a lot of versions of Wm, each version for a unique edge direction and edge label. Okay, so when I multiply hk t minus 1 with Wm, I will retrieve the Wm that correspond to the edge label and edge direction. This is a lookup method for getting model parameters, right? It's slightly different from the standard feed-forward neural network. And we actually saw this method. Where did we see it? We saw it in Neural CRF last week, right? We had a different W matrix for every part of speech label when you calculated Neural CRF features. And this time, this is the second time we see this parameterization trick, okay? So how many Wm's do we have in the end? We have L times 2. This L is the edge label size. This 2 is the direction. Incoming and outgoing. Okay, so this makes our GCN more powerful. And we can still make it even more powerful, okay, by borrowing the idea of gates. All right, so we have a separate gate for every hidden, calculated in a similar way as when we calculate LSTM. And when we do the CNN aggregation in the last equation, as you can see, compared with the last slide, I add a Hadamard product of this neighbor convolution filter with the gate. Okay? That makes the model parameters more complicated and gives the model more representation strength. All right? So, okay, when you go home, you compare the 3 versions of GCN and think about why they are more powerful than the previous version. But now let's move on. We can have graph attentional neural network, okay? So, well, you said I want to collect information from neighbors as my current information, so an attentional function will just do a weighted sum of the neighbor hidden state as the current hidden state, right? So where do the weights come from? Well, we can use the current x as the query, okay? And the previous hidden states as the keys and values. Or whatsoever. I don't differentiate the query and key and value, but basically I concatenate the x, the input representation, and the hidden representation myself and my neighbor, okay? And I put that through a neural network to calculate a score between the current node and its neighbor. And then I use a softmax function to normalize the scores, and I got these attention weights. Are there more advanced versions? Of course, there can be, just as you make your self-attentional network more complicated, okay? We will leave that later. How do you use graph neural networks? Well, it can be the same as you use sequential neural networks. You have a hidden for every node. So when you do classification, you can do an aggregation of the hidden by pooling, etc. Okay? So these are all the graphs. You can use graph neural networks for representing trees and DAGs also, because everything is a graph. Okay? So because you have this powerful tool, GNN, you can try to turn your things into a graph, like coreference, entity mentions of the same thing, okay? Relations, events. You can turn things in a passage into a graph and use GNN to extract useful information for them. Now let's move on to the last section for today. Let's move beyond general graphs and into specific text structures. You know, text have structures for different NLP tasks. A discourse, a passage itself is a structure. When you write a discourse, you know, you have sentences, you have passages, and sentences have words. Itself is a tree structure. But we're talking about text structures for different NLP problems. Let's look at the first problem, which is text matching. The idea is like this. You have two texts, and they form a structure. One example is paraphrase detection. Okay? Paraphrase detection has two texts, and the output is how similar they are semantically. Like if I give these two sentences as I show you on this slide, you have a probability close to 1. Another example of this kind of text matching is text entailment or natural language inference. We saw that in the first week, right? So the two texts are a premise and a hypothesis. You put the two together and the output is whether the premise entails the hypothesis. Okay? So how do you model text matching? I tell you two networks. The first is called a Siamese network. The network is named after the famous Siamese twin. You can look up Wikipedia or ChatGPT about their stories. When you have two texts, you apply an identical neural network or sequence encoder to represent the two texts. Here I just give you an example of BioSTM, okay? And then you have a hidden state for the first one, you have a hidden state for the second one. You put them together and calculate a matching probability. That's a Siamese network. Here is a detailed parameterization. You first turn each sentence into word embedding sequences. And then you use bidirectional LSTM to represent each, as I show you in the slide. In the end, you can use the forward last hidden state and backward last hidden state concatenated together to represent each sequence. I denote them as H1 and H2. Lower. And then you calculate the distance between H1 and H2. For example, you can just use the cosine distance, okay, as the semantic similarity. You need to train the neural network, because without training, the BioSTM encoders cannot tell you who are semantically similar. The training signal will change the BioSTM parameters so that semantically similar sentences will have similar encodings. Now the training data is a set of sentences with gold standard similar or not similar signs. And then when you train the neural network, you can use the cross-entropy loss, as I show you in this equation. Okay? So I don't need to explain them. All right. So this is the cosine way of defining the network function. But you can change the cosine function, of course, which is rule-based, into a network-based similarity function, as I show you in this slide. So that's very familiar to you. That's a standard neuron with sigmoid activation. That also calculates a score between 0 and 1. And you can adjust the model parameters with training. Okay, that's Siamese network. Siamese network has one limitation, which is you encode the both sentences separately without calculating their interaction in the encoding process. And we can actually use a neural network, attentional neural network, to do the matching. Okay? So this neural network turns out to be very useful, also for sequence generation, as I will show you next week. So if you compare the attention matching network with the Siamese network, you can see that one more component is added. Okay? So it's the attentional neural layers. The remaining are the same. I will introduce this attention matching to you. First, the embedding layer is the same as the Siamese network. Second, the hidden representation layer is the same. Now I got something new, which is the attention. What is attention? The basic idea of attention is to, calculate an H1 hat, given H1 and H2. What is H1 hat? H1 hat is a representation of H1, that is aware of H2. How do I calculate H1 hat? I calculate each H1 hat I, or H1 hat for the ith word on the left. I use H1I as the key, as the query, to query every H2J. And I find a weighted sum of H2J as H1 hat. Okay? So I'm calculating a weighted sum of the right sentence to represent each token in the left sentence. That's cross attention. Okay? Equations are like this. I calculate a score, by using H1I and H2J as inputs. And then I normalize these scores across J. And I use the normalized weights to sum up H2J as H1I hat. Okay, and then that can be done in the opposite way. And I got H2 hat as well. So H1 hat is a representation of H1 that is aware of H2, and H2 hat is, one that is aware of H1. Then with those, I can further concatenate H1 and H1 hat as Q1. And I concatenate H2 and H2 hat as Q2. Okay, why do I concatenate them? Because I want to have a version of H1 without being aware of H2, and one version that is the weighted sum of H2, okay? I add both features. And now the next thing I want to do is, I want to turn Q1 and Q2 into one single hidden representation. And that is easy. I can use pooling. And here, I'm using average pooling plus, not plus, concatenated with max pooling. So I'm extracting both aggregation features and salient features, okay? And when I concatenate those for H1 and H2, I get a single vector U. And over this U, I can do the same, just one sigmoid layer to get a matching score, okay? So that's the matching neural network. And you say, okay, the key of attention, cross-attention, is to calculate a weighted sum of the other for representing myself, right? And I do it in both directions. So I calculated two different sets of attention weights. Can I calculate the two sets of weights simultaneously? That is called co-attention or bidirectional attention. Unfortunately, I don't have time to explain all the equations to you, but I just show you the pictures. You can read the textbook, okay? So my idea is, if I duplicate this H1, okay, n2 times, I get an equation which is a tensor, The tensor is thick by dh, the hidden size, And its number of columns is n1. The original dh times n1, so this is h1, right? But I duplicated n2 times. So I duplicate this matrix, the number of word in W2 times, So it becomes a tensor of dh times n2 times n1, okay? If you look at the tensor top down, it's an n2 by n1 matrix, okay? Which is a scoring matrix. So every element in the matrix has interaction between the ith word in n1 and the jth word in w2. Ith word in w1 and jth word in w2. I can similarly duplicate, h2 n1 times to get a similar tensor. Okay, of course I can transpose the tensor, make them similar. And I can do some operations between the two tensors and put everything together. And if I squeeze them into an n1 by n2 matrix, that's a scoring matrix, okay? That calculates the score between every word in the first sentence and every word in the second sentence. And then I can think about how to normalize as to row-wise and column-wise to get the attention scores. I leave it to you to read it, but I tell you the rough idea. The advantage is that we generalize the attention in both directions, okay, into one operation. I calculated one score matrix. Okay, so that's fair in both directions. Now, let's move on to the next section, which is the representation of for reading comprehension. That's another text structure. So, I showed you this task in the beginning. The input is a passage and a question, okay? The output is the answer to the question in the passage. All right. I had this long passage, okay? And there are many, many facts. I denote this passage as W1, the first text. And then I'm giving different questions, right? I can denote the first question as W2. I look in W1 and I found a span that answers W2. Okay? Now I'm given the second question again. I take it as W2. I try to match W1 and I found an answer span. Okay, I can change W2 again and look for the answer. Right? Okay, so this structure is obviously different from the text matching structure. It's non-symmetric. How do I find the answer span? Okay? Basically, I first tell you the basic idea. All right. On the left, I have a representation of W1, the passage. On the right, I have a representation of W2, the question. Okay? All I want to do is to calculate a representation of the passage that is aware of the question. Okay? And when I have that representation, I can try to predict the span. That is the answer. Okay? That's the basic idea. All right? I find a representation of the passage that is aware of the question, and then on top of every word, I try to predict whether this word is the beginning of the answer span or the end of the answer span. That's the thinking, okay? So in the end, it's like a three-way prediction or two-way prediction on every token. Okay, how do I represent the passage? So this is exactly the same as the attention matching network, okay? I ignore that. Second, how do I calculate a representation of W1 that is aware of W2? That is H1 to H2 attention. That can also be the same as the attention matching network, okay? And then I get H1 hat. H1 hat is what I want. And on top of H1 hat, I can calculate U1 by concatenating each H1I and H1 hat I. So I get a representation of W1 with and without W2 information. That's the U1 vector sequence. And then on top of U1, we are ready to predict whether each word is the beginning of the answer span. How do I do that? Okay. Again, I apply a new LSTM on U1, okay? And the result is called MB. It's a vector sequence for predicting the beginning. And on top of every word in MB, okay, I just use a standard softmax output. This softmax output is a two-way prediction. Oh, no. Sorry. The softmax is not a two-way prediction. It's over every word. It's over the sequence. It's over the sequence. So who is the beginning of the answer span? Okay. I first calculate a score for each node by using a model parameter v, okay, called vb, okay, to do the dot product with every element in MB. Actually, in QB. What is QB? QB is the concatenation between MB and U1. Okay? So that's a richer feature. The original U1 feature plus the by ISTM output MB. And after I get all the scores, I use a softmax to find out the highest score. And that's the beginning of the answer span. Then if I know the beginning, okay, I can predict the end on top of it. So I use MB, okay, as the input. And I take another by ISTM to calculate a new sequence called ME. And then I use these ME features, okay, to calculate a new encoding feature sequence called QE. And over this QE, I can predict which word is the end of the answer span. Okay? So the right part, the QE, is built on top of MB. Why is that so? Because MB already contains the beginning of answer span information. So if I stack an LSTM on top of it, I can build the end of the answer span on top of the beginning of the answer span information. All right. So when we have the neural network, I get two sets of probabilities. One set is the probability of the beginning. The other set is the probability of the end. So when we have a set of training data, I can use cross-entropy loss over both the beginning and the end and backpropagate the gradients for training the whole neural network. This is reading comprehension. A last problem for today. Sometimes our reading comprehension goes beyond simple span matching. We need multi-hop reasoning. What do I mean? Let's look at this passage. It contains several facts. First, John went to the office. Second, John left the milk. Third, John went to the bathroom. And the question is, where is the milk now? Okay? How do I find the answer? Of course, one method is just to use the previous network I told you, okay? Represent the passage by looking at the question and then try to predict where the milk is now. But it turns out that normally you want to do some reasoning over the sentences. For example, where is the milk now? You first look at the second sentence, John left the milk. Okay, this is the first evidence. And given this evidence, you want to find the next evidence by looking at the first sentence, John went to the office. And then you predict the answer. The milk is in the office. Okay? So the last thing I want to share with you is how to model this reasoning process. It's a more complicated structure. To make things even more interesting, we no longer predict the span, okay? We just predict one word out of the vocabulary, so that the answer does not have to be exactly in the passage. Of course, you can also understand that as I make the neural network simpler, because I just need to predict one word in the vocabulary. All right, how do you do reasoning? How do I model this reasoning process? We can use a memory network. So this is the basic idea of a memory network. You have a neural network that does the reasoning. And then you have a set of memory. This memory is basically a sequence of vectors. And each vector is something that you remember. Okay? And then the neural network will interact with the memory by sometimes reading things from the memory and sometimes writing things into the memory. Okay? So this is a simple concept of memory network. And we apply this memory network concept to our multi-hop reasoning example. My idea is I take W1, the passage here, okay? And I try to find one vector representation of every sentence in the passage as a memory slot, M1, M2, etc. Okay? So each M represents a sentence in the passage. Okay? And then what I do? I do an attention of this passage representation over the question, okay? To find a question-aware passage representation, this V1, V2 until V and R, okay? So this idea is very similar to the question-answering neural network we saw earlier. And we find, okay, a weighted sum of this V as an evidence vector O, you know. And I use this O concatenated with the Q to predict an answer A. How do I do multi-hop reasoning? Okay? By doing multi-hop reasoning, I just use the current evidence O, you know, to update my question Q. Okay? And I use the new question Q to do a weighted sum of my memory again and get a new evidence O to predict a second answer A. And I can do this over multiple hops and I get an answer. Okay? So that's the basic idea of memory network. And you know, I didn't write into the memory. But I only read from the memory by using Q to query all these memory vectors into an evidence vector O. Okay? Let's look at the network in details. I try to build a very simple version of sentence representation. So this MI is basically just a weighted sum of the embedding of every word in WI. In other words, every memory vector MI, which is the representation of WI in my passage, okay, is very much like a bag of word model. I embed every word in WI and I do a weighted sum. What's the weight? The weight is a scalar position encoding. Okay? I call it Lij. J means the jth word. Okay? All right. So this is very much like a bag of word model for representing a sequence. Can you use BioSTM? Yes, you can. Okay? But I leave it to you to think about it later. So when you have each word represented into a vector M, okay, the whole set of memory is simply M1 until M NR, where NR is the number of sentences in my document DR. Okay? Okay. So I use these memories as a query, a key, okay, as a key. And I use the question Q as a query. I want to find an aggregation of these evidences. To that end, I calculate a set of value vectors. A set of value vectors. The value vectors is again the weighted sum of my word embeddings. But I use another set of embedding matrices, okay? Just to differentiate the key and the value, okay? I used MI as the key. Now I want to use this V as the value. So when I do the query, I use the query vector Q, dot product my memory vector M, okay, to calculate a score. And I use this set of scores to calculate the weighted sum of a context vector V. Okay? Sorry, pardon myself. So on this slide, I'm calculating the representation of the query, okay, which is again a weighted sum of questions in the query. So on this slide, I'm calculating the attention scores, okay, which is a dot product between the query and each memory vector M. In this slide, I'm calculating the context vector, which is the use of another embedding matrix to represent the sentences, okay? So let's look at this picture. I have a document which is a set of sentences. I use one set of embeddings to make them memory slots, M1 and until MNR. So these are the key vectors. I use the second set of embeddings to turn them into V1, V2, and VNR. These are the value vectors, okay? And I represented this question as a Q vector. I'm using the question as a query to query these key vectors, okay? And aggregate these value vectors into the vector O, okay? And then using this O, I can predict the output, okay, by adding the evidence vector O with the query vector as the input vector, and then using a softmax predictor over the vocabulary to predict the answer word. So this is one hop. And then I can do the second hop, you know? The second hop is I use the current evidence vector, okay? Maybe John left the milk, okay? To add to the original query vector. Where is the milk? This is John left the milk. Okay, of course, this is a weighted sum. And I use this as a new query for the second round of the same thing, okay? I have the key vectors, I have the value vectors. I use the new query to query the key to aggregate the values to get a new evidence O. And this time the evidence could be John went to the office, okay? And then I do the same thing to predict the next answer. I can repeat this several times. In the end, the predicted answer is my final answer. Okay, and for training, I have a standard answer word. I can use the cross-entropy loss, okay, for the gold standard answer as the loss function to train the whole memory neural network, which can be seen as a stacked multiple layers of attention functions. Okay, that's it. Let me summarize. In this week, we learned the representation of different structures, including tree structures, lattice structures, graph structures, and text structures. In text structures, we learned 3 networks, basically. So one is a simple text matching network. One is a reading comprehension network, which is non-symmetric. And one is a multi-hop reasoning network. All right. So see you next week.